a quick few words on the disciplinary research area. So the name is Innovation Technology for Sustainable Futures. I mentioned that before. We started setting that up in 2018. And since 2019, we have established this lecture series, which is also called Innovation Pathways to Sustainability. We see that as an opportunity to engage with people that do sustainability research across the world. It's mainly a forum for highly visible at the international scale scientists who are active either in academia or at the science policy interface. And that's precisely the case for Noelle Selin, who is our guest speaker today. Noelle, thank you very much for being here. Just a few words about you. You're an associate professor at the Institute for Data Systems and Society at the Department of Earth, Atmospheric and Planetary Sciences, and also director of MIT's Technology and Policy program. Her research, Noelle's research, uses modeling and data-driven analysis to inform sustainability decision-making. It focuses on issues involving air pollution, climate change, and hazardous substances such as mercury, which is also the focus of the presentation today. Noelle's work focuses, in other words, on atmospheric chemistry of air pollution, and as well on the interactions, and that makes this very interesting for us, between science and policy in international environmental negotiations. Despite her being engaged in numerous international research projects, one of them even in the Peruvian Amazon, where we realized in our preparatory talk that we are working in the same region, she's also a passionate academic teacher, and you will see that because our lecture series has a much more innovative format this time. We will not hear 30 minutes talk straight through. We will have short breaks. You will even be asked to answer a poll. So stay tuned, make sure you get the important content and can participate in those polls. And at the end of the whole session, we will of course have a longer Q&A session to answer all important questions. So this is all I wanted to say. Noelle, if you're ready, I would hand over to you, and I look forward to your lecture and the discussion afterwards.
Great, can everyone hear me?
Yes, okay. I hear you well. I hope the rest hears you well too.
Okay. Well, thanks for that kind introduction and for the invitation. I wish I were able to join you all in Bonn, but I'm really excited to be talking to this group. And I hope that I can convince you with this lecture why the past and present of mercury pollution is not only a challenge that's important to sustainability, but also why it's interesting in the context of innovation and pathways to a sustainable future. So I'm going to draw from the work of my research group at MIT and also from my forthcoming book. And the book examines mercury and the millennia of human interactions with it. And I think it's a really fascinating substance. And we're using the Mercury stories in the book as a way to understand sustainability and also to understand human environment interactions. So I'm going to dive right in and talk about mercury pollution. Mercury is a global scale pollutant, and it poses risks to both human health and the environment. It's emitted to the atmosphere by its intentional use, such as in products and industrial processes, also in mining, and as a byproduct of the burning of fossil fuels, primarily coal. It travels globally through the atmosphere and then deposits to ecosystems. And in ecosystems, it transforms into methylmercury, which is a potent neurotoxin. And since the pre-industrial days, the concentrations of mercury have really increased dramatically. The graph I'm showing on the left is from the Arctic, where it illustrates the mercury concentrations in Arctic biota as a fraction of the present day levels. And you can really see the influence of the industrial age on those concentrations. In 2002, the United Nations Environment Program conducted a global scientific assessment and found that there was sufficient evidence of adverse impacts of human health and the environment from environmental releases of mercury. And that evidence was sufficient to warrant global political action to address these issues. And as a result, 15 years later, the Minamata Convention on Mercury entered into force. And that's a global treaty to address mercury from a life cycle perspective. It was named for the town in Japan where the health effects of methylmercury were first identified in the 1950s. And those health effects are serious, but they also depend both on the form of mercury people are exposed to and the amount of exposure. So many of you might be familiar with mercury in the silvery liquid form, for example, in old thermometers. That's the elemental form of mercury. And people are exposed to dangerous levels of elemental mercury today, primarily in occupational settings. And one major use of that form today is in gold mining. Tens of millions of artisanal and small-scale miners in over 70 mostly developing countries use large quantities of mercury to mine gold. And exposure to mercury vapor at elevated concentrations is dangerous. And some of these impacts have been known for centuries. For example, conditions in mercury mines were well known to be hazardous to workers over 500 years ago. But concentrations of elemental mercury, such as those that exist in the atmosphere, or for example, which you're exposed to if you break just one thermometer, not typically at levels dangerous to human health directly. Although I will say if you break a thermometer, do open a window and dispose of it properly. That's still important. But most people in industrialized countries in Europe and North America are exposed to mercury in the form of methylmercury, that neurotoxin, primarily through diets and largely through fish. And the impacts of most concern of methylmercury are on the nervous system. And in particular, babies born to women exposed to mercury during pregnancy are particularly affected. At high doses, you can get severe damages, even death can occur even in adults. This occurred in that Japanese town of Minamata starting in the 1950s. But at lower doses, those to which many more people are exposed, pregnant women and babies are the most vulnerable, those damages involve cognitive development and development of the nervous system. And the statistic I'm showing here is from the United States in the early 2000s. It was estimated that more than 300,000 babies were born every year to women whose mercury levels exceeded the guidelines that were intended to protect against those adverse neurodevelopmental effects. But if you're not a pregnant woman or a child, mercury can also affect other systems. It may even cause cardiovascular impacts, such as heart attacks in all adults. So really everyone has to be concerned or thinking about mercury. This is the most recent atmospheric emissions inventory for mercury. So mercury emissions continues. The largest emissions are in Asia, where coal use in China and India is particularly high. Mercury emissions in the US and Europe have declined in the past several decades as a result of emissions controls. Some emission control for other air pollutants also reduce mercury emissions, and these controls and others have been implemented in several countries. You can also see the footprint of artisanal and small-scale gold mining, particularly in the tropics, in Northern South America, for example, in Peru and across Africa. But the total magnitude of this source is uncertain. Nevertheless, it's estimated that this is the most recent inventory, and between 2010 and 2015, there was a 20% increase estimated in global mercury emissions. So it's continuing to be a problem. An important note, though, is that mercury is not just a present day problem, it's an element. So as an element in the periodic table, it's impossible to get rid of. But mercury is further unique because once it's emitted or released, it continues to cycle for centuries or longer between the atmosphere, land, and ocean. And this is my virtual tourism slide because it shows pictures of places that I was able to visit before we did all our travel on Zoom. And on the left is a picture of a sushi plate that I had in Japan. And I'm using that to illustrate that today's piece of tuna contains a combination of some small fraction of naturally occurring mercury, mercury emitted recently, so today's power plants and artisanal mining, but also mercury that was emitted decades to centuries ago that continues to cycle in the environment and also accumulate in fish. And those historical sources stretch back centuries to millennia. The picture on the right is from the Almudena mine in Spain that operated for over 2,000 years, and it only closed in 2002. It's one of the few major mercury mines that operated worldwide. And I actually visited it last January, one of my last trips before the pandemic. They mine cinnabar. This is cinnabar ore. You can see that here, this kind of reddish rock. And it's now a UNESCO World Heritage Site, but over its history, it produced 250,000 tons of mercury. And its mercury in the 1500s was exported to South America, where it was used in silver mining during colonial times. And that mercury it's uncertain its environmental fate, but it may still be circulating. So the connection between mercury, food, and mining and gold and silver should give you a sense of how mercury is intertwined with a number of issues of broader relevance to sustainability and human well-being. This figure comes from the UN Development Program. It identifies the Sustainable Development Goals of relevance to the mercury challenge. The link to safe fish comes in through goals 2, 3, and 14. Artisanal mining raises questions about poverty and economies, goals 1 and 8. Energy through affordable and clean energy through the link to coal and coal burning. And consumption and production, mercury's use in a broad variety of products and processes, both historical and in the present day. So this connectedness in history makes mercury, in my opinion, a good case to look at how people have managed their interactions with this, what's a simultaneously very useful, but also very dangerous substance. And this was really what prompted us to write Mercury Stories. In this presentation, I'm going to focus on two questions. The first, understanding the mercury challenge itself. And the second, drawing broader lessons for sustainability more broadly. And I'll show a variety of methods and approaches that my group uses to help understand issues like mercury pollution that are relevant to human well-being across a number of dimensions. So many studies on mercury examine its behavior and impacts by focusing on what's going on in the environment. And this is similar to other kinds of pollution studies, focusing on geological, chemical, and biological processes, a typical biogeochemical cycling approach. What I hope the introduction showed you is that it's really impossible to understand the mercury challenge, like other sustainability challenges, without looking at the entire system. And that system doesn't just involve environmental components. It also involves technologies, technological components, power plants, production processes, mines, built infrastructure. And those can, for example, lead to emissions. And what's in the environment affects people and their communities, so humans. But it's not just a linear system of technologies, environment, people either. People react to impacts, and through increasing knowledge and building institutions, they in turn modify technologies and modify the environment. So to fully understand the mercury challenge, we need to address all 5 of these components: humans, technology, the environment, institutions, and knowledge. So in our book, we set out a new framework and analytical approach. We call that the Human Technical Environmental Systems Framework, or the HTE framework. And that's really designed to give some structure in addressing the many elements of mercury as a systems problem. The HTE framework and its associated approach, which uses a matrix-based formulation, gives a roadmap of 4 distinct steps to break down these types of issues. A first step is to identify the relevant components of the system, which we divide into the 5 categories I talked about on the previous slide. We found in our research that using all of these 5 categories were necessary to describe the important dynamics of 5 different mercury-related cases we examined. I'm going to show those on the next slide. The human, technical, environmental components, we treat those as material. That is, they involve material or physical phenomenon, think about things. Institutions and knowledge, the other 2, those are non-material. And you can think of each component having associated attributes that describe it, for example, location, size, age. And so once we identified those components, that's where the matrix comes in. We construct a matrix of rows and columns with each of the components identified and then describe their interactions. We focus on the material components, which interact in the context of institutions and knowledge. So this is a sample matrix shown here on the slide, in which there's 1 human component, 2 technical components, and 3 environmental components. We just use this as an illustration. The shaded squares indicate the presence of interactions, and you can see that those are affected by institutions and knowledge. So once we've mapped out those interactions, we can then look at changes in them, intentional efforts to alter the system, hopefully towards sustainability, through identifying interveners, those agents that act upon the system, and their interventions to change components and their interactions. And this analysis in the final step can be used to draw insights and lessons. So these are the 5 mercury-related systems we examined in the book. Each is the focus of a chapter. So here I'm going to focus on the human health system, and then I'll pause for my poll and a few questions. And then I'll go on to part 2, where I'll address issues of energy, industry, and pollution. So part 1, you can expect maybe about 20 minutes, part 2, maybe about 15 more minutes, just so you can moderate the Zoom fatigue here. All right, so I'm gonna launch right in to part 1 and talk about human health. And to motivate that question, I wanted to start with a question that was asked of my research team right as we started a study looking at the impact of mercury and other pollutants. We were working with Native Americans in the US state of Michigan, and we were working together with researchers at Michigan Tech University. And this community was the Keweenaw Bay Indian community. And for them, fishing and eating fish was important to their culture. But these fish had high levels of mercury. And we held a stakeholder workshop with them at the beginning of our project. And they said, well, if the fish have high levels of mercury, here are our questions. Where's this mercury coming from? Is it coming from local, regional, or global sources? What can be done? What is being done? What effect will all these policies have? And ultimately, what does that mean for our community on the ground? When will these fish be safe to eat and under what conditions? So based on this introduction, you might already be thinking that answering their questions involves considering all 5 of the categories of components I talked about before. So you can think of this as an example of how to evaluate the system involving mercury and human health. I'm going to generalize this a bit beyond the local community and talk about mercury and human health more generally. So first of all, the community both harvested and consumed their own food from their land. So they're a human component here. But others buy food on the commercial market. Those buy fish in supermarkets, and that food is produced by others. The ecosystems where this food comes from, they can be near mercury sources, can also be far from mercury sources. And the food involved is largely fish and shellfish, but in some places marine mammals are important sources of food and contamination, like in the Arctic. And in other areas, like in China, rice can have high levels of mercury as well. So mercury comes into these ecosystems through industrial uses, such as, for example, in production processes. And both emissions and releases, as well as the process of harvesting and providing food, occurs in the context of national and local laws and regulations. Dietary recommendations, who should eat what and what quantities, such as the advisories that nearly all waterways in the United States are subject to due to mercury contamination and also other pollutants. Cultural norms, this is the case in the Indian community where consumption of fish was part of a traditional diet. And the Minamata Convention has a particular focus on human health. It's the first multilateral environmental agreement with a dedicated health article. Knowledge is also an important piece. Forms and properties of mercury, exposure, routes, concentrations, and what the health impacts are. So the next step will be to map out the interactions between the components. I'll illustrate this by giving you a couple of examples. So let's start with 2 of these components, mercury in production processes and ecosystems near mercury sources, just to give you an idea of how this works. So mercury in production processes can influence ecosystems nearby when mercury is released or emitted. And this interaction occurs in the context of national and local laws and regulations, which might, for example, set some guidelines or ban such releases. We can summarize this qualitatively as industrial uses of mercury contaminate ecosystems near sources. And then we can put that into the matrix format, where the element in the row, the industrial source, influences the column, the ecosystem. And then we can identify a couple of more interactions. The ecosystems near and far from mercury sources affect the fish, shellfish, and other animals that live in them. And in particular, ecosystem processes can transport mercury, lead to methylmercury production, and then accumulation in these fish. And these foods then affect people, potentially damaging the health of those who harvest or purchase food from those ecosystems. And then we can put those interactions in the relevant categories in the matrix, where the environmental components are interacting with each other, and then the environmental components influence the human components. Importantly, these interactions link together in a pathway in which industrial uses of mercury contaminate ecosystems. That mercury is then transported and transformed into methylmercury, and then it accumulates in seafood that leads to health damages. That's what's happening in general terms. And to dive into the details of these processes, these descriptions can be associated with a number of more detailed methods, and those you can implement quantitatively. So to quantify past, present, and potential future emissions and releases, my group has used a variety of techniques, including engineering analysis, interviews, literature reviews, scenario development. To simulate the transport of mercury in the atmosphere, my group uses a tool called GeosChem. It's a global scale, finely resolved 3-dimensional model of atmospheric chemistry and transport. And that can tell us how mercury travels from place to place geographically and the chemical reactions it undergoes. And we've linked this tool to ecosystem models which simulate the production and accumulation of methylmercury. And then on top of that, we can also layer on exposure and health impact analysis, really looking at the entire pathway. But this pathway is a simplified version, and those 3 interactions are part of one of the more complex pathways that we identify in the book. So in the book's treatment, we also include the process of harvesting mercury-contaminated food, and also the fact that seafood and rice can lead to health benefits. In particular, fish contain important nutrients, polyunsaturated fatty acids, that contribute to brain development. And the impacts to people ultimately can depend on their biology, as well as socioeconomic factors, such as whether they're economically able to switch to other sources of dietary protein. So the next step in the process is to look at interventions. We can think about 3 different ways of addressing mercury-related health issues. such as those that were of concern to the Kimono Bay Indian community. And the first is regulating emissions and releases. A second, addressing where and when people can fish and where they can sell fish. A third is dietary advice for consumers. This needs to take into account both the potential harms and benefits, encouraging people to eat healthy fish, not avoiding fish altogether, and also be sensitive to cultural and local contexts. So these three types of actions occur at different places along the pathway and can be implemented by different actors, different interveners. So to give you an example of how to evaluate the prospects for interventions, I'm going to talk in the next few slides about how to trace the impacts of emissions regulations through the system and what they imply for exposure. And I'm going to give you an example from the US as well as a global example from the Minamata Convention. So I'll start with the United States example. Back in 2012, the US Environmental Protection Agency announced the mercury and air toxic standards. And those were standards that regulated mercury for the first time directly from coal-fired power plants. And this is the then regional administrator speaking at an event in Boston when they announced the standards. And as I mentioned before when I talked about emissions, mercury emissions from coal burning have declined quite a bit in the last few decades in the US. But that's because other air pollutants were regulated. And the technologies that were used to address this other air pollution, particulate matter, also reduced mercury pollution. Mercury emissions were also regulated specifically from waste incinerating sources in the 1990s. But in the 2000s, mercury contamination was still a problem, for example, for communities like the Native Americans in northern Michigan. And despite the bonus reductions that you get from other air pollution controls, coal-fired power plants were still the largest source. So the mercury and air toxic standards regulated them directly. And for the most part, they required power plants to implement mercury-specific controls, so technologies that were specifically designed to capture mercury before it was emitted. So take a look at the figure that's on the stand next to the administrator, and I'm going to zoom in on it on the next slide. Okay, so that figure comes from a study that I did that looked at the fraction of mercury depositing to the US that comes from sources within relative to outside North America. So as I said before, mercury is a problem across the US. Nearly every waterway has an advisory about eating fish from it due to mercury contamination. But that source of that mercury differs. And this is because mercury is emitted from polluting sources in a few different forms. So one of those forms travels long distances, and one of them rains out quickly. And thus mercury is both a local and a global problem, as well as a near-term and a long-term problem because of its continuing cycling once it deposits. So we did this analysis using our global atmospheric chemical transport model. So for your navigation, here's northern Michigan, and here's Boston. The relevance of this is the following. For the people who harvest fish in the orange and red colored areas where the largest fraction comes from North American sources, that mercury is primarily coming from coal-fired power plants, which are just upwind. So controlling that mercury would go a long way to solving their mercury problem, eventually by reducing inputs. But for people in northern Michigan, places where mercury was also depositing, leading to fish advisories, this wasn't solving the problem. Most of their mercury is from international sources, potentially power plants as far away as India and China. And people in the US, of course, eat fish from the global oceans as well. So you really need a two-pronged approach, both domestic and international. And the Minamata Convention is that international way of addressing those emissions. Here's a picture of a group of MIT graduate students I took to the final negotiation session of the convention. That was back in 2013 when the treaty text was finalized. So what we were interested in doing was tracing through the impacts of these two different policies to deposition in the US and all the way through to health impacts, following the pathway I talked about earlier. And this involved creating emission scenarios consistent with the two policies, both the domestic mercury and air toxic standards and the global Minamata Convention. And then we used our global model to calculate the resulting deposition. So what you can see from the two graphs above, the domestic standards are on the left. They reduce deposition in some areas of the US quite a bit. In the global policies on the right, you can see this more widespread decrease. We then used information on exposure to compare the impacts of this on US seafood consumers. And we quantified the damages avoided, the impact on cognitive development via avoided IQ points lost for newborns, and also for the entire US population on heart attacks. We're then able to use an economic model, and our results are shown in the lower right, to quantify the avoided damages to the US economy. And we found benefits of these regulations in the billions for the domestic standards, and that's in purple, and in the tens of billions for the global standards in green. And we also made sure to examine uncertainties on each aspect of this complex pathway and how those models interacted. And that's shown by the different lines in the lower right graph. But that's not the end of the story. So the rule, which was announced in 2012, was subject to legal challenges, and that challenge went all the way to the US Supreme Court. And we did our work and published it in 2016, 4 years after that rule was announced. The original proposal that the US Environmental Protection Agency had issued a few years earlier acknowledged that they didn't actually know how to do this quantification, which we didn't do till 4 years later. So the scientific methodologies and tools available at the time in 2012 really weren't up to the task. So EPA conducted a partial analysis of mercury benefits, and they decided to quantify benefits only for people who catch freshwater fish themselves, so recreational fishers and their families, and only for a subset of the health benefits, so the reduced IQ. And so this partial calculation, the benefits amounted to $4 to $6 million per year. But the costs of the rule overall were in orders of magnitude in the billions of dollars. And this disparity was seized on by the US Supreme Court, which pushed the rule back to EPA, telling them that they should reevaluate the proposal in light of the differential costs, which they estimated in the billions, and benefits, which they said were in the millions. But of course, we had new results that contradicted that. So in 2016, our results were taken into account as the EPA revised its finding, and they said, well, those cost estimates aren't enough to change the determination. And one piece of supporting evidence for this was our study, which showed that there were billions per year in benefits. But another important factor was the issue of environmental justice. The overall benefits to the entire country were, of course, important, but the burdens of mercury pollution fall particularly on certain groups, subsistence fishers, for example, Native Americans like the community we worked with in Northern Michigan. So we wanted to dive in and look at the impact to those communities. And to do this, we linked our atmospheric model to ecosystem modeling to look at this in detail. So we projected mercury concentrations for the lake that this particular community was fishing in. And we looked at 3 different policy scenarios. We looked at what we called an aspirational scenario that was really aspirational. It completely zeroed out anthropogenic emissions. And that decreased fish mercury by 2050 by 65%. And we also looked at the current policy and action scenario, and that led to an 11% decrease. But importantly, none of the modeled scenarios were projected to reduce fish mercury concentrations to the target that would be safe for the local tribe before 2050. So what does this mean? First, that both emissions policies, interventions upstream, and dietary advice, those downstream interventions, are necessary at the same time. But also it really draws attention to the timescales of the mercury issue, the continuing legacy that's both circulating in the global environment as well as in those ecosystems themselves. And that introduces kind of a lag time in the system. Just illustrating how this lag time happens with a simple schematic, the mercury that's already in the global environment at the present day continues to cycle. So if you stopped emissions right away, that historical component would decline over time. If there were no historical component, you had constant emissions of mercury. What goes up must come down. There would be constant deposition. But what's happening in the real world is that blue line where even if you had constant emissions, you're still feeding that system so that the historical legacy component continues. And so we've broken down that blue line into the historical and the new component. And that really shows the long-term nature of the problem. This is not too different from some of you may be familiar with the dynamics of the carbon cycle. So this means that the longer emissions reduction are delayed, the more historical mercury there is in the system, because you're kind of feeding that with time. And this has differential impacts. We actually examine this effect using our model. And here we're showing the degree to which the impacts of policy reduce when you take into account that delay. So for example, let's say you're implementing a policy that if you did it today, it was a result of a certain percentage decline in emissions. Every 5 years you delay that, you lose a certain fraction of that effectiveness. Eventually, it's like doing nothing at all. Your deposition is the same as it would have been today, despite the fact that you've taken action to cut emissions. And that's because of the historical emissions that happen in the meantime. And so that fraction that you lose ranges up to 20%, depending on where you are in the world. And if you're nearer to sources, you'll feel this less, because most of your deposition will come from nearby present day sources. But if you're in remote locations, such as the Arctic, you'll feel that more. And unfortunately, there's still some policy delay. It's a characteristic of policy processes. Under the Trump administration, the US Environmental Protection Agency has reevaluated that 2016 finding that reinforced the basis of the mercury and air toxic standards rule. By the way, this has actually already been implemented by the relevant industries, so this is also a policy puzzle. And the Trump administration found, and this is a legal term, that it's not appropriate and necessary to regulate emissions from coal-fired power plants. And in doing so, they repeated the claim that there are only millions of dollars in benefits. And in order to do that, they really basically said, well, since this study, they dismissed our study because, well, it was a model and we actually did uncertainty analysis. And since we did uncertainty analysis, of course, these benefits are very uncertain. So you have this institutional retrenchment that's happening, which in turn affects the environment. And of course, this isn't really the correct way to look at an uncertainty analysis. So I'm still trying to do my part to communicate the results of our work in the hopes that our findings are used accurately in the regulatory process. And this is a picture last May of testifying before the US Congress on this work. So going back to the mercury and health system, I want to conclude the part one of my talk by highlighting some of the broader conclusions that came out of our examination of health issues from the book. And this gives you a flavor, I hope, of the kinds of insights we can draw from the mercury work that are more relevant more broadly to sustainability issues. First of all, mercury is a dangerous substance, but understanding its impacts really requires looking at the interactions with technology and society. For example, environmental processes intersect with cultural factors, dietary choices and recommendations, as well as these policy pathways. And the impacts are simultaneously global and local. Second, process of transitioning to sustainability and sustainable human well-being really depends strongly on issues of valuation. The ways in which overall assessments of value in the US legal system are implemented can feed back to influence the disparities in exposure that already exist. And third, that effective governance of mercury health risks involves integrating strategies from local to global and also applying different types of interventions. Those that involve different points on causal pathways, and also those that integrate and are sensitive to socioeconomic factors. So with that, I'm going to do a short pause and a poll to get some of the more fun and fascinating flavor of the historical nature of mercury as a substance. And so while you think of a few questions to ask, I'll give you a quiz. Which of the following was not a term used by alchemists to refer to mercury? We talk about alchemy in the book. As late as 1924, alchemists claimed to have found a way to turn mercury into gold. Is it mother egg, secret furnace, venomous dragon, silver fox, or green lion? Of those five, 4 of them were used by alchemists to describe mercury. We can see what that is. All right, it looks like you're divided between whether it wasn't silver fox or green lion. I think I'm gonna end the poll here and give you the spoiler that silver fox is actually not a term used by alchemists to refer to mercury, despite mercury being silver. All of the other ones were alchemists' terms. So any clarification questions or other discussion before I go on to part 2?
Well, thanks for now. So now we have the chance for 5 minutes to make some technical follow-up questions, and at the end of the talk we will have a longer question and answer session, but for now we have the opportunity to ask some questions. Okay, there's one question from Jan. You can say it by yourself, so you're here.
Yes, I can do that, and I can be seen. So I was wondering, you talked a lot about the benefits of reducing mercury emissions. How do those compare to the costs, like the technical possibilities of doing that? And is there something like a risk of, if you regulate mercury emissions strictly in industrialized countries, that the industrial activity that causes it shifts to other places where the environmental governance is rather poor?
I think there's 2 ways of looking at this. So the costs, again, in the United States were estimated in the billions, but those were really advanced mercury controls, very mercury-specific controls. And those controls were really only used in, this is the highest level of control in the world, really. Under the Minamata Convention, I'll talk about this in part 2 a bit. So countries can actually put regular air pollution controls, so the things that will control sulfur, particulate matter. And those are of reasonable cost compared to those kinds of costs that were the very advanced mercury controls, and they'll actually do a lot to reduce mercury emissions. So there's always a risk, of course, that regulating emissions in industrialized countries shifts industrial activity. The Minamata Convention is trying to avoid that by establishing that all countries that are parties have to use best available technologies to address those emissions. But there are cross-border flows in that way. There was a recent study for China that a lot of the Chinese emissions of mercury were actually for products for export. So similar to other environmental issues, this is certainly an issue for mercury as well.
So another question. If not, I have one.
Okay.
It was not entirely clear to me why you choose mercury for your research. Is it because mercury is the most relevant, or at least a relevant factor in pollution and the consequences for human health, or is it because this kind of estimation can serve as a best practice example with respect to other pollutions or elements like CO2 or nitrate in groundwater or whatever?
So I think for two reasons. One is the large political interest in mercury, the regulations, both domestically and internationally. In terms of international activities, the Minamata Convention was the first new multilateral environmental agreement in 2 decades. So that was this first standalone agreement. So there was certainly a lot of activity on mercury and a lot of global concern associated with mercury. I do work on particulate matter and other air pollutants as well as other toxic pollutants. But I think one of the unique things about mercury as a topic for the book is just this millennia-long history. So you really have mercury not only just emitted, but actually also used in a variety of products and processes. And so it's not only an air pollutant, it's also a product. It's also sort of a cultural factor, and just thinking through that really gave us a lot of rich empirical material to look more broadly at how sustainability transitions over time were conducted.
Okay, and what is your impression? I mean, I'm referring to the second possibility of my question. I mean, in Germany, at least, we are talking a lot about CO2 and other greenhouse gas emissions. And obviously, this is very strong related to mobility, and Germany as a car producing industry is very important, of course. So do you think it's transferable, your kind of investigation to other questions?
So I think you've introduced my second part, if I can.
I'm sorry.
So maybe this is a good time to launch into. I have about 10 minutes on energy industry and pollution and okay, some of the connections to climate change. So we can just go ahead and do that.
Yeah, please.
All right. All right. So can you see my screen again? All right. You can see my part 2.
Yes, everything is
Great.
Visible to me. Yeah.
Perfect. All right. So I'm going to just show you some of the technical issues that can affect emissions control and how they propagate through the system. So to do this, I'm returning here to the type of visualization I showed you earlier on pathways. And here's the pathway that involves pollution control and mercury emissions. So air pollution control devices, as I said earlier, can be designed to capture mercury and other air pollutants. Some of these, especially designed to capture sulfur pollution, also capture mercury. Some are mercury specific. So applying these reduces emissions, but also incurs costs, which are passed along, for example, to energy consumers. Once that mercury is captured, though, it has to be dealt with appropriately so it doesn't get released to the environment elsewhere. So one type of intervention is to mandate that specific controls be applied, usually by governments. And there's a provision in the Minamata Convention that relates to this. And as I said, that involves best available techniques. But what's clear in the way the requirement is stated is that countries have some flexibility in implementing these, and also in determining what's both technologically feasible and available. And so to look at this question in more detail, we did a study focused on China and India and focused on the power sector. And in order to do this, we did a series of in-depth interviews with policymakers and technical experts to determine for the power sector in both China and India, what technology controls under best available technologies would look like under two different interpretations of this flexible requirement. And then we used engineering-based analysis to project associated emissions under these scenarios. And what you're seeing here is the three scenarios: a no emission additional control scenario, a scenario where you implement the Minamata Convention very flexibly, and then a more stringent implementation where you ratchet up sort of one notch the kinds of technologies you're using. And the power sector emissions are shown here in color, and this is projected out to 2050. Blue for China, red for India. In the gray, we held the rest of the sectors constant. Focus on the three ones to the left for now. And so remember I told you that the power plants emitted in forms deposited locally and traveled globally. Those are the different colors here. The darkest here is the form that travels globally. So under the more stringent policies, emissions decrease from the power sector. And this isn't really surprising. But what is surprising is that the forms that decrease are particularly the ones that deposit locally. And this is especially the case in India. So that's where the more stringent policy comes in. But then what we did was we assumed for all of these, an underlying emission scenario. And then we applied an energy use scenario. We applied another energy scenario in which the energy mix was much less reliant on coal. And we got lower emissions overall. And that difference was bigger than the delta in policy. And again, that's for the power sector specifically. And we can actually further calculate the difference that this interpretation of the control requirements makes in deposition. And what I'm showing here is the difference it makes to go from that minimal interpretation to something a little bit more stringent. So the extra deposition that would be avoided with a bit more technology. And those are substantial. And those differences are largely accruing domestically to India and China. And that suggests this is in the global interest, of course, but also substantially of interest to those countries themselves. But what we were interested in, results of that study, particularly on the energy sector, raised a broader point. And that's really what was raised in the Q&A, the influence of a fossil fuel economy on the mercury problem. And I'm illustrating this in another pathway diagram where fossil fuels enable operation of those industrial sources, produce energy and industrial goods, providing important benefits to people, but nevertheless are emitting lots of different pollutants. And of course, for climate change and energy transformations, moving away from fossil fuels is vitally important. And you can think of that as a potential intervention as well in the mercury system. But unfortunately, it's also politically challenging. So if I think about the Minamata Convention, which came into force in 2017, and the Paris Agreement, the Minamata Convention would not be enforced today if it relied on reducing fossil fuels to mitigate mercury. That negotiation never would have gone forward and gotten as many countries to agree as it did. So we're interested in how these things interact. So our end of pipe control technology is really just yesterday's Band-Aid solution, not worthwhile to do when you have this energy transition going on. How do we think about these things together? And how do we understand and model their interactions, both technologically and societally? So that was the impetus for the study, which was published earlier this year. And we used an economic model together with our atmospheric chemistry simulations to develop scenarios and to look at the impact of the Minamata Convention and the Paris Agreement together. And we focused on China. We looked at all sectors, not just the power sector. And so we have some emissions scenarios here. And I'm just showing emissions, although we did propagate all the way to deposition in the study. And we have the levels of emissions in 2012, then no control scenario for 2030. And then that third from the left is the Minamata Convention policies. The three in the middle are different climate greenhouse gas control scenarios, the middle of which is consistent with China's commitment under the Paris Agreement. The one to the right, a little bit more stringent, the one to the left, a little bit less stringent. And then the combined scenarios are on the right, the Minamata and Paris combined scenario, and then the scenario that ratchets up the climate commitment a little bit. And one of the conclusions we had was that, without any controls, emissions would increase to over 1,000 metric tons by 2030. And climate policies under the Paris Agreement would reduce this to 1,035 metric tons. But air pollution controls implemented to meet the requirements of Minamata would have a much bigger effect, reducing mercury emissions to 533 metric tons per year. But when they're applied together, you did get some synergies. Mercury emissions fell to 490 metric tons per year. And a more stringent climate target could get rid of another 20 tons. But importantly, that was less than additive, because what happens is the end of pipe controls reduce the benefit of eliminating the source entirely. But this also raises some important questions about prioritizing the near term versus the longer term. So there's a couple of dynamics that are at play here. So if end of pipe technologies are implemented, this might have the effect of lengthening the lives of new plants and make climate policies more difficult to achieve. But in North America, we've actually seen the opposite effect. Increased stringency of emission controls has encouraged early retirements of power plants, particularly those old coal burning plants. So what I take away from this is that pollution control very much still matters. That the climate policies that are being talked about and implemented now, they don't just take care of other issues like pollution that are a result of things like coal burning. And that you can't really just reduce the sustainability challenge to just CO2 or energy transition alone. If you emphasize that, you don't actually see some of the near-term trade-offs and technology and policies that influence human well-being in the nearer term. So leads me to a summary slide on the insights from our chapter on energy industry and pollution in the Mercury book, and then I'll go on to a broader concluding slide on the book more broadly. And what emerges from the case we looked at in Mercury was that really these incremental actions, these small changes, not just the big transformations, they had substantial benefits for human well-being. And this was both in the near term as well as in the longer term, because remember, reducing mercury actually reduces that historical component. And this was true in history, and it's also going to be true going forward. And so it suggests that they really shouldn't be overlooked in a focus on the increasing need for very transformative change, that these two things have to happen together in order to enhance human well-being. The second thing is that the interactions between policies in these different sectors are both physical and societal. So from a technical perspective, they weren't additive, they addressed different sectors, but they were also politically related through common frameworks for negotiations, and that poses a challenge for implementation. And that also raises the challenge of how to manage that governance of the possible. So obviously the efficient technical solution to the mercury and climate problem together would be just get rid of coal. But this creates political problems in the near term. And the question is, what is the pathway to get there that minimizes the climate and the dangerous mercury effects? So maximizing those realistic benefits to well-being is both a near-term and a long-term challenge, both for those of us who assess these problems from a technical perspective as well as implementation. So I wanted to sort of close by highlighting a few overall thoughts and potential ways forward. So what I hope I've convinced you in these two different parts is that the approach, the HTE framework, is a useful one that's able to address the complex nature of issues that relate to sustainability, and to link broad thinking about systems to concrete methods to examine interactions and potential interventions. So try to show the beginnings of how we can use such thinking to start to build theories and to draw broader insights. But we absolutely need more cases and more empirical examples in this broader field that can be compared to each other. So I wanted to invite the audience to apply such a framework in your favorite case and to get in touch if you're interested in doing so, because I think the goal of all of this work is not only to understand these systems and understand these pathways and transitions, but also to inform action at all levels and by everyone to improve human well-being around the world today and in the future. And mercury, as I said, is only one of the many challenges that's important. The goal of my research more broadly is to inform the solutions that can make people's lives better. So with that, I'm going to stop and take any questions and discussion. Thanks.
Okay, thanks, Noelle. Thanks a lot. Yeah, now we have to do the possibility to discuss. Are there any questions? Yes, Janos Schwester, please.
Hi, good day, everyone. Thanks, Noelle, for the very, very cool presentation. I enjoyed it a lot, using that as an example for broader systems interactions and environmental pollutions and which actions we can take. Fascinating. So I, as a political scientist working at the Center for Development Research together with Jan Berner and a research project there, I've heard a lot of complexity in that. Basically, maybe that's the word that sums up or can sum up one of these main lessons there. So temporal, spatial, especially temporal, I found interesting, technological, and regulatory. So looking at the Minamata Convention and thinking about when we have banned a couple of decades ago the harmful substances, FCKVs, fluor, and other air pollutants. That was one of the last successful conventions that I can remember, and that seems to have also had some impact now, which you nicely traced back. And one of your recommendations was how to integrate from global to local level in terms of policies and regulations, as our socio-ecological interactions, they span the globe on this giant ecosystem. So incremental governance and the series of small wins, these parallel processes that need to happen. What would be your comment to that, aligning regulatory global and local governance systems or regulations? Thanks.
Thanks. That's a really great perspective to think about how that how the governance levels interact as well. And one of the things that I think is really interesting about the Mercury case is that you have these actions at very different levels of governance, that, you know, the hyper local, the communities on the ground. And, you know, I didn't talk about the new project that we have with an artisanal and small scale gold mining community in Peru. But, you know, people around the world that are dealing with very, very local pollution issues that are also simultaneously a global challenge. And that, for example, dietary advice, there's generalizable knowledge about the dangers of mercury, but those need to be really targeted to the kinds of things people eat, the ways in which they consume it. For example, some of the dietary advice that the Native American community that I worked with was using was, well, here's how we actually consume fish. We fillet it and put it in the freezer, and you can mark where the fish was harvested to get a lake by lake guidance of which ones should maybe not be consumed by younger people or pregnant women. And the knowledge that, you know, people do freeze these things, right? So the advice was write it on your package in your freezer, right? And that's very specifically hyper local, but you also have a global framework, and that intersecting levels of governance intersects with the physical realities of the mercury problem in ways that are both environmental. So mercury obviously transports globally, as I showed, but also mercury is traded globally. So you have this, you know, trans-border trade that had mercury historically coming from Europe and going to South America and fueling global trade processes. So as you think about sort of the governance required, there's an aspect of capacity building. There's also an aspect of just getting these levels to work together, and sort of understanding the problem. And it's also at the same time causing some challenges. For example, a lot of the impacts that countries are interested in are the local impacts. And they want assistance from the global treaty to deal with those and monitor those local impacts. But that doesn't necessarily fit with some countries' ideas of what a global treaty is for. So I think those are some of what I would say are the political challenges and really interesting sort of ongoing research questions going forward.
Thank you.
Okay, thank you. Another question?
I don't have a blue hand because I'm a co-host, so I'm raising my real hand.
Okay, Jan, please.
One question, you talked about, you know, relationships with the Paris Agreement and the whole climate change debate. And in that debate, there's sometimes this fear that if you give up on mitigation, if you put more emphasis on adaptation, people might give up on mitigation. And I'm wondering how much adaptation is possible to circumvent the mercury problem by, you know, just stopping to eat certain fish or fish from certain areas or whatever. Is that an issue in this mercury debate as well, or is there no way to actually adapt out of it? You have to reduce the sources.
So I think that the key point here is that it plays out very similarly to the climate debate, in that, of course, for those who are sort of more privileged and have more economic opportunity, there are certainly ways that you can mitigate your risk. For example, if don't eat tuna sushi 5 times a week, that's something that someone can reasonably do. Or pregnant women living in Germany can choose healthier fish in order to minimize their mercury exposure. The real challenge is that a lot of people don't have that choice. For example, subsistence fishers, people living in places where they're highly dependent on fish as a source of protein. And some of these communities have some of the highest mercury exposures. So I think there's an awareness that those two things go together. And I think that's very similar to the kinds of challenges that we see in climate, that certainly there's some things that you can do to adapt to the problem, and some things that are going to be required because mitigation won't be fast enough. But also an awareness that continuing delay in mitigation does make the problem worse going forward. And that was part of what we were thinking about as we thought about the policy delay question, because I think that lag time is really important in thinking about how you're feeding a future problem.
Thanks.
Okay, thank you. Some more questions? Yeah, and I think I can hand over to you.
Okay, no, if there are no further questions, which I almost cannot believe, think about it for another second. If not, Janos again, go for it.
Hi again, yes. The Minamata Convention, it is a not very well known convention, not very popular convention. Could you maybe add some information, some background brief on the how it came into force, and what are the signing or signatory parties, and is it binding or non-binding or something like that? Thank you.
Sure, absolutely. And it has actually a long history. So I skipped over from the 2002 global mercury assessment to all the way to 2013, and I didn't really explain. It is a global legally binding treaty. And in 2002, when the global mercury assessment came about, the other convention that is not as well known to the broader field is the Stockholm Convention on Persistent Organic Pollutants, and that was signed in 2001. And the UN Environment Program Chemicals Division said, okay, so they had actually negotiated the Rotterdam Convention on Prior Informed Consent up until 1998. 2001, the Stockholm Convention, it was sort of a question of what's next. And the issue of mercury was a substantial sort of issue of long-range transport. Mercury was also covered under the Convention on Long-Range Transboundary Air Pollution. They had a protocol on heavy metals and persistent organic pollutants, and that's again in the started negotiation in the early 1990s, finalized in the late 1990s. And so there was regional action on mercury as a transported substance, increasing evidence from modeling and from data that this was an important problem, particularly in remote locations such as the Arctic, and also in countries that had ongoing issues with mercury in the developed world. But what happened in 2002 is that there was sort of shortly thereafter, 2003, 2004, there were proposals at the UNEP Governing Council to go ahead with a legally binding agreement, but countries didn't agree at that time. And so European countries very pushing quite heavily for a legally binding treaty, but other countries not so much. And in particular, the United States played a substantial blocking role at that time under the Bush administration, which was very skeptical of global multilateral environmental cooperation. So what happened at that time was that they launched a mercury program, a voluntary program that was sort of the different coalitions of countries along with non-governmental organizations and with industry to address the mercury issue in a voluntary way. but it repeatedly came up at the UNEP Governing Council every couple of years. And gradually the coalition built, countries in Latin America and Asia realized they had a problem with artisanal mining. And so that coalition built, and in 2009, it was actually the first act of the Obama administration that came in the United States that changed the US position. And that really tipped the scales in the UNEP Governing Council. China and India were still a bit skeptical, but they said, well, okay, let's push off the start of negotiations for another year till 2010. And so they started negotiations, had 5 different international negotiating committee meetings. I went to 3 of them, I think, maybe 4. And then the treaty text was finalized in 2013. It needed 50 parties to enter into force, and that threshold was reached in 2017. We've had 3 conferences of parties since then. Number of parties is up to about 100. So conference of parties, the 4th one will be next fall, fingers crossed, for that we are all traveling to Indonesia at that point. But that's sort of the history. It's an entire life cycle convention. So it deals with sort of production, bans mercury mining, trade, mercury in products, so phases out a bunch of uses of mercury in products that have substitutes. Again, has that article on health, emissions, and releases as well. And also has an article on artisanal and small-scale gold mining, the typical capacity building and other financing issues in it. So it's a full multilateral environmental agreement.
Okay, thanks. There's another question. JP Emmons from BMU, please.
Hi, can you hear me?
Yes.
Okay. Yeah, my question was regarding the coordination and cooperation between different agreements. You were talking about the cooperation interaction between, for example, the climate change agreements, the mainly economic repercussions of the agreements together. Is there anything similar regarding or concerning the agreements on biodiversity or species protection in the marine environment, for example? Do you have any insights on that in that regard?
So not so much, and that's interesting in and of itself. So again, mercury in collaboration with the other chemicals agreements have been quite a lot. Obviously there are some physical linkages with the climate change negotiations, not so much on the political level, again, because of this need to sort of distance itself from the political controversy and actually get something done on mercury. On biodiversity, that's interesting. So I've spent a lot of time, obviously not this summer, but in previous years at the Technical University of Munich. And I co-supervise a graduate student there who, one of her main interests is thinking about how the potential synergies between the chemicals conventions and the biodiversity conventions are going forward. And that's sort of from a political science perspective, but we don't have results of that project yet. But I think there's a lot of potential. One of which is sort of in the pesticides and sort of foods area, but also obviously mercury has some potential intersections as well, thinking about wastes and other aspects.
Okay, thanks.
Thank you.
So
there's no, if there's no other question, I have maybe one final one to you, more from the perspective of our whole TRA, which is members who are into, behavioral economics, nutrition sciences, agricultural sciences, remote sensing, chemistry, but also medical sciences. So if you were to say, okay, I need a few disciplines to engage with in order to push some frontiers in mercury science, what are you thinking? What are you thinking about? Where would you go and expand your research? Maybe through this planetary health lens that we talked about in our previous conversation. What are sort of, if you dream up new ideas, where would you want to go, and what would be your ideal collaboration partners in which areas? Not necessarily here in Bonn, but generally.
So one of the really interesting things about the mercury issue is, so I've been working with the Minamata Convention. It has a provision about monitoring the effectiveness of the convention. A lot of the work that we've done in the past on mercury and on other substances really been sort of, what are the prospects for potential future policy. But at some point, hopefully, we're going to get to the point where we've actually implemented these policies and really tried to monitor and adapt. And wanting to really document the impact not only on people and their health, but also trace that back to whether the policy intervention is effective or not, and use that as a kind of learning process. And I think, so some of my more recent work has been trying to look at some data science tools to do that, working with health experts. So we have a project looking at what exposure to a broad range of types of substances are, and sort of whether that shows fingerprints in people's basically in cells, and whether that can be used as a potential monitoring device of people's exposure to different air pollutants. Eventually, that's a sort of pie in the sky goal. But the idea is to understand what people are exposed to using these models, and then use that information and data to kind of talk back not only to the emissions and what's in the atmosphere, but also all the way back to using collaborations with people who think a lot about causality and, for example, economics and behavioral economics of what actually can be attributed to policy and not. And so there's a couple of things that mess up that signal. If you think about that in the Mercury case, ideally, what I hear from the effectiveness evaluation group, the technical expert group that I was part of at the Minamata Convention, is, well, okay, so we're just going to monitor mercury concentrations in people, and then if they go down, then the treaty is effective. And clearly that's not right, because people are making different decisions, and they might be changing their diets. The concentrations in those fish that they're eating can change because of mercury policy, but they can also change because of climate change, or because those fish are changing their diets because of availability of different species and ecosystems. The deposition can change because of policies, but also can vary year to year because of differences in meteorology or long-term change. And then playing back, those emissions decreases may have been the result of policy, but also may have just occurred anyway. So that's the sort of economist part of that. Can you actually attribute something to an actual policy or not? And in order to ask this practical question, is the treaty effective? You really need to integrate that. And I think that's one of the most important things going forward in the sustainability transitions area, to think about how do you monitor and inform smart policies going forward, taking into account also the politics of that, not just the technical aspects. So yes, that's a multidisciplinary challenge and needs collaborations from all of those things that you identified.
Great. Okay. Yeah. Thank you very much. Okay, colleagues. So I don't see any other blue hands or people waving frantically behind their screens. If that's the case, then once again, Noelle, thanks a lot. We'll be in touch after the lecture once again. And thank you everyone who is still on the call for coming and listening in. And we hope to
want to say that, give an invitation to anyone to contact me. Otherwise, I know that, had I actually gotten a chance to visit you on campus, we might have had some informal conversations, and those who think about questions later. So I'm happy to have any individual conversations with the people who are interested in sustainability more broadly. So just an open invitation. I know the Zoom format is a little weird sometimes for that.
That sounds great. Yeah. So keep that in mind, please. And we hope to meet you again in the next lecture, but join me in clapping virtual hands once again for Noelle. Thank you so much.
Well, thank you again for the invitation.
Okay, thank you. Bye-bye.